If the stars above you slowly faded night after night, would you notice the moment the universe began to come undone? Long ago, Buddhism used a quiet but unsettling image. Worlds don't last. They form, endure, decay, and vanish. Not only people, but mountains, oceans, the sun and moon, everything that feels permanent, eventually slips away. I'm not here to preach or turn this into religion. I'm bringing up that ancient echo because modern cosmology, with telescopes and satellites and cold measurements, is arriving at a strangely similar mood. In the last century, we learned the universe is expanding. We measured an afterglow from the Big Bang. We mapped galaxies across billions of years. And what these dry numbers keep pointing to is not a universe that stabilizes forever, but one that evolves in a single direction. From a remarkably ordered beginning toward a future where structure thins out, energy spreads, stars burn out, and darkness becomes the default. Not with a bang, more like a slow exhale that never stops. In this video, we'll walk through that story step by step from the first seconds after the Big Bang, through the era when stars were born at their peak, into the age of black holes, and finally the endgame possibilities. The big freeze, the big rip, and what they would actually feel like from the inside. Stay to the end, because the real question isn't only how the universe ends, it's what it means to live inside a story that fades. So let us stay with that fading story a little longer, not as an audience waiting for an ending, but as someone quietly noticing that the set itself is coming apart between scenes. When people talk about the fate of the universe, they usually imagine a final event, a last explosion, a last collapse, a last frame. But if the universe is slowly undoing itself, the unsettling part is not a single catastrophe. It is the thought that unmaking could be woven into every moment that feels completely normal. Imagine a sweater that no one is pulling on. No visible hand, no impatient gesture. Just a loose thread at the cuff that catches, here and there, on the world. Each time, a few loops slip free. The fabric still holds. The sweater still warms you. Yet row by row, the pattern thins, until one day you hold it up to the light and realize you can see through it. When cosmologists speak of the universe undoing itself, they mean something like that. Not a film running backwards into the Big Bang, but a long erosion of every pattern the universe has managed to knit together. Galaxies, stars, planets, temperature differences. Even the arrangement of matter itself, all of it drifting toward a state where nothing stands out enough to be called structure. On the surface, the universe does not look like it is coming apart. It looks busy. Stars form. Planets circle. Black holes collide and ring space-time like a bell. From our small perspective, there is motion everywhere. But underneath that motion is a direction. We give that direction a simple name: entropy. It is the tendency for things to spread out, to become less special, to take on arrangements that are easier to arrive at by accident. A hot object cooling in a cold room, ink dispersing in water, a memory losing detail whenever it is recalled. The details differ. The trend does not. Expansion is the stage on which this happens. When we say the universe is expanding, we are describing the geometry. On the largest scales, distances between unbound things grow with time. Space itself stretches, like the fabric under the sweater. That by itself is not undoing. It is a change of scale. Undoing needs more ingredients. You take expansion. You add entropy. You fold in the life cycles of stars, steadily burning the simplest fuel into heavier ashes. You include dark energy, the mysterious pressure that seems to push galaxies apart faster and faster. Together, they do not just give a universe that becomes larger. They give a universe that, step by step, loses the contrast that once made it dramatic. We know this not because of poetry, but because of very old light. In mid-July of the year 2022, an image was unveiled at a press event in Washington. It looked, at first glance, like glitter spilled on black velvet. Tiny points, small smears, arcs of distorted light. It was given a hopeful name: Webb's first deep field. Inside that tiny patch of sky were thousands of galaxies, some whose light began its journey when the universe was only a small fraction of its current age. We were not seeing a still life. We were looking at a time-lapse. Deep fields like that let us look back along the path the universe has taken. In that single image, patterns are layered. Nearby galaxies with settled spirals. Distant galaxies, still clumpy. Background arcs stretched by gravity into thin curves. A universe very good at making structure. A few years later, another picture was released. This time it was a composite. Infrared from Webb, optical light from older telescopes, and X-rays from orbiting observatories. The combined view showed around 1,678 galaxy groups and clusters in one frame, some bound tightly, others only beginning to gather. One of the most crowded portraits ever taken of cosmic structure. If you glance at that image, it looks like evidence against undoing. So much is still there. So much is still happening. But the same physics that allows those clusters to exist also sets the timer for their separation. As space continues to stretch, many of those groups will drift so far apart that, in the far future, their light will never reach one another again. The Webb tightens locally, even as it frays globally. This is what makes the idea of self-undoing feel so impersonal. There is no external force that dislikes complexity and comes to wipe it away. The universe does not need a reason to fade. It only needs time. Given enough of it, every process that builds something also contains the terms of its own failure. Stars are a clear example. They create heavy elements, planets, and in at least one case, the conditions for beings like us. But every second a star shines, it is converting organized fuel into less useful forms of energy and radiating that energy away. The light that makes life possible is also the signal that some potential for future arrangement has been spent. A star is a machine that pays for local order with a larger increase in disorder elsewhere. Entropy is not magic. It is a way of counting. In the early universe, there were fewer ways for matter and energy to arrange themselves while still looking the same on large scales. The cosmos was hot, dense, almost uniform. As time went on, the number of possible microarrangements grew. Gravity pulled matter into lumps, igniting stars and carving out voids. Nuclear reactions added new particle species. Collisions scrambled energies and directions. From one angle, that looks like progress. More variety, more storylines, more ways to exist. From another angle, it is a slow dilution of distinction. In the very long run, as energy spreads and temperature differences even out, what remains is not a single pristine order, but a fog of possibilities in which no particular pattern stands out. There can still be an enormous number of microscopic states, but almost all of them correspond to the same macroscopic reality: thin, cold radiation, with no clear characters left. So when we say the universe is undoing itself, we are not invoking reversal. We are pointing to this drift from an extremely special beginning toward a future where almost everything looks statistically ordinary. The temporary islands of structure between those two extremes are what we call galaxies, stars, ecosystems, minds. Day to day, our sense of reality is built from stable rooms, reliable streets, familiar screens, recurring faces. The scale of our attention is small, and within that scale things do seem to persist. Projects can last years. Buildings can last decades. Civilizations can feel ancient. It is easy to treat them as foundations, and ourselves as the change that moves across them. Cosmology quietly inverts that picture. From its point of view, it is the large-scale behavior that is relentless. Space will keep expanding, entropy will keep increasing, Stars will keep aging. Structures will keep slipping from probable to fragile. We are the brief interruption, the thin layer of organization that appears on the surface of a planet for a fraction of cosmic time, then vanishes. From the perspective of physics, the process is unthinkably slow on human scales. No global catastrophe is scheduled for tomorrow. The stars we see tonight will still be there for many generations. The great unraveling happens over spans of time so large that we describe them with phrases like raised to the power of, rather than ordinary counting words. Yet, the direction is as firm as any law we know. The universe does not get younger, it only gets older. And somewhere inside that long, patient decline, on a small world orbiting an ordinary star, we are trying to understand what it means to be temporary, in a universe that is, itself, gradually losing the ability to make anything last. To even ask what it means to be temporary, we have to look back to a moment when almost nothing existed that could be called a thing at all. The story we usually tell about that moment has an explosive name: Big Bang. It sounds like fireworks. It sounds like something that happened somewhere, at some time, inside some pre-existing emptiness. But the picture that has slowly emerged over the last century is quieter and stranger than that. What we call the Big Bang is not an object going off inside space. It is space itself changing, every point moving away from every other point, distances stretching, time beginning to have a direction. If you had been there with a ruler, there would have been nowhere to stand outside the event. The ruler, the space, and the event would have been the same unfolding process. It is unsettling to realize that our language is built for things that happen in rooms: storms, arguments, births, funerals. The Big Bang is not that kind of thing. It is the reason there are any rooms at all. A century ago, people were not thinking in those terms. For a long time, many astronomers assumed the Milky Way was the entire universe. The faint spirals and smudges on photographic plates were called nebulae and filed under objects inside our galaxy. The sky looked large, but conceptually it was still small enough to feel contained. On an October night in the early 1920s, an observer at Mount Wilson pointed the Hooker telescope toward one of those smudges, the Andromeda Nebula. On the glass plate, a particular star stood out. It changed its brightness in a regular rhythm. That rhythm marked it as a Cepheid variable, a kind of star whose pulsations reveal its true luminosity and, with that, its distance. When Edwin Hubble did the calculation, the result was too large for comfort. Andromeda could not fit inside the Milky Way. It had to be a separate galaxy, an island of stars far beyond our own. The universe had quietly expanded in our minds, long before we knew that it was expanding in reality. That expansion became harder to ignore at the end of the same decade. In the late 1920s, Hubble plotted the redshift of galaxies against their distances and found a pattern. The farther away a galaxy was, the faster it seemed to be receding from us. The points did not fall perfectly on a line, but the trend was clear. Space was not static, it was stretching. It is tempting to imagine that discovery as a dramatic overturning, but in practice it was a graph, a set of dots and a slope. The idea that the universe might have once been smaller and denser flowed from that slope as simply as water running down a channel. If galaxies are moving apart now, then earlier they must have been closer. Follow that reasoning far enough back, and you arrive at a time when the distances were so small that the familiar notion of galaxies stops making sense. The Big Bang concept grew from that seed. At first, it was an extrapolation. Later, it gained a specific, testable prediction. If the universe began from a hot, dense state and expanded, then there should be a leftover background of cooled radiation filling all of space. In the middle of the 1960s, two radio astronomers in New Jersey found it by accident while trying to get rid of noise in their antenna. The static would not go away. It arrived from every direction, with almost the same intensity. Eventually, others recognized it as the cosmic microwave background, the afterglow of a time when the universe was filled with a hot plasma, and light could not travel far without being scattered. Only after a few 100,000 years of expansion did it cool enough for electrons and protons to combine into neutral hydrogen, making the cosmos transparent. That transition, and the light released at that moment, are what we still see today as a thin bath of microwaves surrounding everything. The numbers behind that sentence are easy to state and hard to hold. The recombination of matter into neutral atoms happened roughly 380,000 years after the Big Bang. The oldest light we can see now has been traveling for more than 13.5 billion years. The background is chilled to a temperature only a few degrees above absolute zero. We package those statements into words, but each one points to conditions so unlike our own that our intuition has almost nothing to grab onto. Maps of that background glow show something else important. The temperature is astonishingly uniform, but not perfectly so. There are tiny variations. At the level of roughly 1 part in 100,000, slightly hotter spots, slightly cooler spots, slight differences in density. Those imperfections are the seeds of everything. If the early universe had been exactly the same everywhere, gravity would have had nothing to work with. There would have been no slightly denser patches to collapse into the first stars and galaxies, no way to turn smoothness into structure. The existence of those small fluctuations means the early cosmos was not just hot and dense, it was hot and dense in a very particular way. Here is the part that quietly unsettles many physicists. In terms of entropy, that early state looks incredibly ordered. Gravitationally, it was almost as simple as it could be. A nearly uniform sea of matter and radiation, with only tiny ripples. The number of possible gravitational configurations that would look like that on large scales is staggeringly small compared to the number of ways the same amount of matter and energy could have been arranged in a messy, clumpy, high-entropy way. In other words, the universe seems to have begun in a state that was not generic. It was special, ordered to an almost impossible degree. This is not a mystical claim. It is a statement about counting possibilities. If you think of all the ways the contents of the universe could be set up, the overwhelming majority correspond to situations where matter is already clumped. Black holes already dominate, and there is no simple, nearly uniform background to speak of. Instead, we find ourselves in a cosmos where the early conditions were just so. Smooth enough to give a clear arrow of time, irregular enough to allow gravity to magnify tiny differences into galaxies. From that starting point, more than 13 billion years of evolution have unfolded. Radiation cooled. The first atomic nuclei formed within the first few minutes, locking in a particular mix of hydrogen and helium. Later, as the plasma thinned and neutral atoms formed, light decoupled and began its long journey to us. Gravity, slow and patient, tugged slightly denser regions into still denser structures. The Dark Ages passed into the first starlight. It is tempting to see that sequence as a climb from simplicity to complexity, from a plain, featureless beginning to a universe rich with variety. There is truth in that, but if you keep the second law of thermodynamics in the back of your mind, the story feels different. The very processes that build complexity also increase entropy. Nuclear fusion in stars releases energy and spreads it into space. Gravitational collapse, counterintuitively, can raise entropy by turning smooth distributions into clumps plus heat. The early low entropy state is what makes all later structure possible, but it is also what guarantees that structure cannot last. This is where the phrase, ordered to an impossible degree, matters. If the universe had started off in a typical high-entropy configuration, there would be no arrow of time in the way we experience it. No broad trend from ordered past to disordered future. No thermodynamic gradient for life, weather, chemistry, or memory to ride on. A cosmos that began in a bland equilibrium would, in a sense, have no story. Instead, we live in the aftermath of a very unlikely arrangement. The universe began in a state that could unroll into stars, planets, and eventually beings capable of noticing the unrolling. It is as if the film began in a single, carefully composed frame, and the following scenes are what happens when you let that frame relax. The numbers that anchor this picture are, by now, surprisingly precise. Measurements of the cosmic microwave background's temperature pattern, combined with observations of galaxy clustering and the rate of cosmic expansion, point to an age for the universe of about 13.8 billion years. That span is long enough for small quantum fluctuations in the early plasma to grow into the web of clusters we see today. Long enough for multiple generations of stars to live, die, and enrich space with heavier elements. Long enough for one rocky planet around one average star to host beings who build detectors sensitive enough to take the universe's baby picture. There is a quiet irony in that. The more accurately we measure the universe's age, the more we confirm that we live in a very particular slice of its history. Old enough that the cosmic background is cooled and stretched into microwaves we can map. Young enough that the sky is still full of galaxies, and the background has not yet faded beyond detectability for any conceivable radio telescope. Somewhere between the first light and the last. From the perspective of entropy, that slice has a simple interpretation. The universe began in a low entropy condition that allowed an arrow of time to emerge. As time passes, entropy increases, and the space of possible states the cosmos can occupy grows. Early on, that growth manifests as structure, stars forming, galaxies assembling, temperature gradients appearing. Later, the same trend drives the decay of those structures. Eventually, if our current models hold, the universe will approach a state where almost all remaining possibilities are macroscopically indistinguishable. Thin radiation, sparse matter, little left that could serve as a memory medium for anything. The Big Bang, then, is not just the start of expansion. It is the moment when this entire trajectory is set, a beginning that is strange specifically because it is so clean. From that smoothness, everything else unfolds. The making of suns and planets, the rise of chemistry and biology, the emergence of minds that can wonder why the initial conditions were what they were. In that sense, the universe is a machine that both builds and breaks itself. The same rules that let it grow structure also ensure that structure is temporary. The same improbably ordered beginning that allows for meaning to arise guarantees that meaning is not backed up anywhere outside the patterns that briefly hold it. We often comfort ourselves with the idea that what is deeply real must be what lasts. Cosmology suggests almost the opposite. What lasts, in the largest sense, is not form but tendency. The pull from low entropy to high, from special configurations to generic ones. The intricate shapes that appear along the way, galaxies, biospheres, languages, personal histories, are byproducts of that pull. Beautiful, consequential, and, on cosmic scales, fleeting. And here we are, in one of those fleeting patterns, trying to trace the entire arc back to a beginning we cannot visit, inferring it from a thin bath of microwaves and the slow drift of galaxies, and realizing that the ordered start which made us possible also set the direction toward our eventual erasure. That direction has a quiet name in physics, but you have felt it your whole life, long before anyone told you the word. You do not need cosmology to notice it. You see it in a mug left on the table. Fresh coffee, steaming, then slowly cooling until it matches the room. You see it on a shelf when a glass slips and shatters. Pieces fly outward. They do not gather themselves and leap back into your hand. You see it in a bedroom that is lived in. Clothes and books drift outward from their original places. Left alone, the room acquires detail, not symmetry. On some level, we treat this as obvious. Of course coffee cools. Of course broken glass stays broken. Of course messes accumulate. But if you took a single frame from any of those scenes and showed it to a physicist, the deep laws they write down would not tell them which way the story is supposed to run. The equations that describe gravity, electromagnetism, and quantum fields are almost indifferent to time's direction. Run them forward or backward, and they still make sense. A film of planets orbiting could be played in reverse, and nothing in Newton's law would complain. A simulation of atoms colliding in a box would be allowed to trace its steps back as neatly as it went forward. At that level, the universe does not come with a preferred before and after, Isabros. And yet in lived reality, everything we care about does. We remember our childhood and not our old age. We can spoil milk but not unspoil it. We can burn a book in a second, but we cannot, with the same ingredients, reassemble the exact sequence of letters that were lost. Something about the way the universe is organized makes certain directions in time easy and others, for all practical purposes, impossible. The word we use for that something is entropy. Entropy is not a mystical force. It is a way of counting. Take a system you can describe from far away: the amount of gas in a room, the average temperature of a cup, the total energy of a galaxy. For each of those macroscopic descriptions, there are countless microscopic arrangements that would look the same to you at a glance. Entropy is, roughly, a measure of how many such arrangements are compatible with what you see from a distance. High entropy means there are many possible internal states hiding under the same outward appearance. Low entropy means there are relatively few. When all the air in a room happens, briefly, to be crowded into one corner, that is a low entropy state. There are not many ways for all the molecules to conspire to do that. When the air is evenly spread out, there are vastly more possible microscopic configurations that count as evenly spread. So the uniform case is high entropy. It is not that the air prefers it, it is that almost every random arrangement looks like that. The second law of thermodynamics lives here. It says, in its calm way, that for an isolated system, entropy does not spontaneously decrease. It can stay the same. It can increase. But if you see it go down in some small region, it is because you have pushed the change somewhere else, raising entropy more in the surroundings. On the whole, over time, the number of accessible microscopic arrangements tends to grow. In the 19th century, as steam engines and industrial machines pushed heat and work into the center of human life, people began to notice that this law had unsettling consequences. If entropy always rises in a closed system, then a universe that had existed forever should already be at maximum entropy, smeared out, equilibrated, without gradients left to exploit. The fact that we see stars burning and waterfalls falling and winds blowing suggested something odd. Either the universe had a beginning, or our understanding of thermodynamics was incomplete. Physicists like Clausius and Kelvin leaned into the first option. They imagined a future where all usable energy would eventually be degraded into unstructured warmth. No temperature differences, no free energy to drive engines, weather, or thought. They called it heat death. In that vision, the arrow of time pointed toward an eternity of nothing happening, a universe that had used up the sharpness of its contrasts. From a planetary kitchen, this heat death starts as a tepid cup of coffee. But life exists in the gap between those extremes. A human body is a local pocket of low entropy that stays so by taking in structured energy and sending out degraded energy. Food comes in as concentrated chemical potential. Waste leaves as diffuse heat. A plant receives sharp sunlight and re-emits softer infrared. A civilization burns fossil fuels to power city lights and dumps extra heat into the air and sea. Every island of apparent order is an entropy machine, exporting more disorder to its environment than it removes from itself. Stars do the same on a larger scale. A star might look like a simple glowing sphere, but internally it is a furnace that turns low-entropy nuclear fuel into higher-entropy ash and radiation. The bright rays that can nurture life on nearby planets are also the signature of entropy being pushed outward, step by step, into space. From this angle, the arrow of time is not an extra rule laid over the universe. It is a statistical trend baked into how many ways things can be arranged. The reason you never see the smoke of a fire gather itself and crawl back into unburnt logs is not that it is strictly forbidden by the microscopic equations. It is that, among the unimaginably many possible configurations of molecules, the ones where the smoke spontaneously reassembles are so fantastically rare that, for the life of the universe, you can treat them as impossible. The cosmos could, in principle, have been different if it had started in a generic, high-entropy state, where matter and energy were already distributed in a way that looked like equilibrium. there would be no clear gradient to run down, no natural way to distinguish a direction in which entropy increases, no thermodynamic arrow of time. Without that gradient, the kinds of processes we associate with a flowing time, growth, decay, memory, evolution, would be difficult to define, let alone to sustain. Instead, as we have seen, the universe seems to have begun in a low entropy configuration, at least as far as gravity is concerned. That choice of initial condition is what makes it possible for entropy to climb. The arrow of time, as we experience it, is not written in the microscopic laws alone. It is carved out by where the cosmos started and the fact that there were many more places for it to go than to stay. In the 20th century, people began to explore what that meant, not just for steam engines and stars, but for the entire fate of reality. One of the clearest meditations on this came not from a physics textbook, but from a short story written in the mid-1950s. In it, Isaac Asimov imagined a series of scenes stretching from a near-future Earth to the edge of cosmic time. In every era of that story, humans or their descendants, or the machines that inherit their questions, ask a version of the same thing. How do we reverse entropy? Each time, the answer is that the data are insufficient. Each time, civilization advances, spans grow, stars are rearranged, machines become more subtle. And each time, entropy continues to rise. Worlds cool, stars die, the universe thins. Only at the very end of that fiction, when everything material has decayed and only a kind of abstract computational ghost remains, does the question receive an answer. It is framed as an act of creation, a new beginning born from total dissolution. The story is not a physics proposal. It is a parable about our refusal to accept that some processes are one way. Reality, so far, is less generous. Modern physics knows of no mechanism that would globally lower entropy for the entire universe. Local decreases happen all the time in a growing embryo, a forming crystal, a galaxy condensing from a cloud, but they are always paid for by larger increases elsewhere. Proposals for cyclic universes, where expansion is followed by contraction, and perhaps by a new Big Bang, have to confront this accounting. If entropy carries over from one cycle to the next, each new universe would start more disordered than the last. Where, then, do we get the clean beginning required for an arrow of time to emerge again? Some speculative models try to dodge this by invoking strange symmetries, or by suggesting that what we call past and future are just two halves of a larger, time-symmetric whole. Others imagine that, near a bounce, new physics would reset the entropy somehow. These ideas are interesting, but they are not yet grounded in evidence. They are ways of probing a simple discomfort, that our universe seems to be a one-shot process, with no built-in restart. When you take entropy seriously beyond the lab, the arrow of time stops being just a classroom topic. It becomes the background slope under everything. It nudges hot stars toward cold embers, fresh planets toward geological stasis, living bodies toward decay. It shapes not only physical processes but what can be remembered. You can store a memory by creating a pattern in neurons, in ink, in magnetized bits, but keeping that pattern stable requires constant work against noise, against the tiny erasures that accumulate when many microscopic possibilities jostle for space. Some philosophers and physicists talk about a psychological arrow of time. We feel time as moving from remembered past to unknown future because our brains are entropy machines, taking in sensory information, burning metabolic fuel, and laying down traces that can be reactivated. Those traces are thermodynamic records. They exist because entropy increased during their formation. In a hypothetical universe where entropy did not grow, memory as we experience it would be hard to define. All of this makes the notion of undoing more concrete. The universe does not just happen to go from tidy to messy. It is drawn that way by the sheer imbalance between low entropy and high entropy configurations. There are vastly more ways for a system to be broken than to be intact, more ways to be lukewarm than to be sharply hot and cold at once, more ways to be forgotten than to be remembered. From this point of view, The long-term picture of cosmic evolution is not mysterious. Start with a low entropy beginning. Add laws that allow structure to form and energy to flow, and entropy will rise. Early on, that rise builds the scaffolding for galaxies and stars. Later, the same rise erodes those structures, dilutes their energy, and pushes the universe toward homogeneity. What we call history is the intermediate phase, where the swing between those regimes is most dramatic. In everyday life, the arrow feels gentle. Coffee cools. Rooms clutter. Metals rust. On cosmic scales, the same arrow is ruthless. It turns bright star clusters into fields of cooling remnants. It turns colliding galaxies into diffused halos. It turns black holes, eventually, into faint baths of radiation. At every step, more of the universe's energy budget ends up in forms that are harder to organize into new patterns. We sometimes talk about progress as if it were a law, that things will get better, more complex, more advanced. Entropy offers a quieter counterpoint. Complexity can indeed grow for a while, locally, in pockets that feed on gradients. But there is no guarantee that this trend continues forever. There is only the broader drift towards states that occupy most of the available phase space, states that, from far away, all look essentially the same. So when we say that the universe is slowly undoing itself, the arrow of time is the mechanism underneath that sentence. It is why there is a direction to our stories at all. From low entropy to high, from special to typical, from crisp beginnings to blurry ends. The question that remains, and that we will carry into the cosmic timeline, is simple and not at all comforting. Given this arrow, how has the universe used its brief allowance of low entropy so far, and how far along that one-way slope have we already slid? If time has a slope, then the universe has been sliding down it for a very long while already, and the only way to feel that motion is to walk back through the moments when the darkness first learned how to shine. In the earliest scenes, there is no night sky to stand under. There is no sky at all. Just a hot, dense, glowing plasma where light cannot travel far before being scattered. Everything is so tightly coupled that there are no separate objects yet. No stars, no planets, no empty voids between them. Just a kind of blinding fog. As this young universe expands, the fog thins and cools. Over hundreds of thousands of years, the average energy of the particles drops. Eventually, protons and electrons can finally stay together long enough to form neutral hydrogen atoms instead of being ripped apart again. When that happens, light is suddenly free to move. Photons that used to bounce around as if trapped in a crowded room now stream outward, mostly unimpeded. Those photons did not stop. They have been traveling ever since, their wavelength stretched by the expansion of space. Their color shifted from searing brightness into a faint wash of microwaves. When we build sensitive detectors and aim them at the sky, we can still register that afterglow, a near-uniform background of radiation, a reminder of the moment when the universe first became transparent. Seen from that perspective, the universe began its visible life by letting light escape. But transparency is not the same as structure. After that decoupling of light and matter, the cosmos enters a kind of long, slow pause. Astronomers call it the Dark Ages. And the phrase is literal. There are no stars yet, no galaxies. The hydrogen and helium gas left over from the Big Bang fills space almost evenly, with only tiny variations in density. Gravity feels those variations and starts to amplify them, but it works on vast timescales. For a long time, nothing would have looked like anything. If somehow you could drift through that era, there would be no points of light to steer by. Only a diffuse, coldening medium, slightly denser here, slightly thinner there, quietly being rearranged by its own weight. Very gradually, the denser patches win. Regions with just a little more matter pull in more of their surroundings. Over millions and then hundreds of millions of years, clouds collapse, fragment, and finally cross the threshold where nuclear fusion can ignite. The first stars are born. This moment has its own poetic name: Cosmic Dawn. Those earliest stars were probably nothing like the Sunday. formed from pristine hydrogen and helium, with almost no heavier elements to cool and fragment the gas efficiently. They are thought to have been extremely massive, extremely hot, and extremely short-lived. They pour out ultraviolet light, carve bubbles in the surrounding gas, and begin to reionize the universe, stripping electrons from atoms, turning the dark ages into a patchwork of growing, glowing regions. In that era, entropy is already at work. The gravitational collapse that forms a star raises entropy by converting a smooth distribution of gas into clumps plus heat and radiation. The nuclear reactions in the stellar cores drive entropy higher still, turning simple nuclei into heavier ones and bathing the cosmos in high-energy photons. But because the starting state was so uniform, the early universe can afford this. There is a long way to go before the gradients are used up. As more stars form and die, they leave behind enriched gas laced with carbon, oxygen, silicon, iron. That gas cools more effectively, collapses into new generations of stars, some lighter and longer lived. Around some of those stars, disks of material assemble into planets. The simple initial conditions, under the guidance of gravity and thermodynamics, begin to write a more complicated script. The small, early galaxies that host these processes merge and grow. Their shapes evolve from irregular clumps into disks and spheroids. Interactions tug out tidal tails, stir gas, and trigger fresh waves of star formation. In this middle act, the universe starts to look more like the one in astronomical images. Rich in shapes and contrasts, a web of luminous knots connected by filaments and separated by dark voids. Somewhere in this unfolding story, there is a period which astronomers now call cosmic noon. The metaphor is deliberate. It is the time when the universe is most intensely busy with building stars. By reconstructing the history of star formation from deep surveys, we infer that the rate at which new stars were born rose from very low values in the earliest epochs to a broad peak when the universe was only a few billion years old. At that time, on average, galaxies were forming stars roughly 10 to perhaps 100 times faster than they do today. Gas supplies were more abundant and more easily funneled into dense, star-forming regions. The cosmic economy was in full expansion. If you could stand in a galaxy during that noon, the sky might have looked more crowded. Giant star-forming complexes would blaze in ultraviolet. Supernovae would punctuate the darkness more often, each explosion seeding the surroundings with heavier elements. Supermassive black holes at galactic centers would feed more greedily, their accretion disks shining as quasars bright enough to outshine their host galaxies. Even from our late vantage point, we can see hints of that intensity. When telescopes look at galaxies whose light has been traveling for more than 10 billion years, we often find systems that are clumpy, turbulent, thick with gas. Some are forming stars at rates hundreds of times higher than the Milky Way does now. Others, intriguingly, already seem to have turned off star formation, their gas exhausted or heated to the point where it no longer collapses easily. They are old before their time. Cosmic noon is not a sharp instant. It is a broad plateau in the history of star formation, spanning perhaps a couple of billion years. Before it, the universe is ramping up, learning how to make complex structures efficiently. After it, the overall pace of construction slows. Gas reservoirs are depleted or locked away in stars and remnants. Feedback from supernovae and active black holes stirs and heats the remaining gas, making it harder to compress. The cosmic factory does not close, but it moves from frantic expansion into a more measured, declining phase. This is the part that can be easy to miss when we look up at the current sky. To our eyes, the universe is still full of stars. Every clear night, away from city lights, the Milky Way stretches overhead as a dense band. Through telescopes, galaxies appear everywhere, at all distances. It feels like an ongoing story, but the data tell us that, on average, the universe has already passed its most productive age. The main burst of star birth is behind us. We live not in the dawn, but in the long afternoon. The numbers that go into that statement are not abstract. The age of the universe, according to our best models, is about 13.8 billion years. Cosmic noon happened roughly 2 to 3 billion years after the Big Bang, which means it lies around 10 to 11 billion years in the past, relative to us. In other words, the universe spent only a minority of its current lifetime in that peak building mode, and we arrived long after that peak was over. There is a strange asymmetry in how we observe this. When we look at nearby galaxies, we are seeing the universe as it is now, older, quieter, with star formation generally reduced compared to its peak. When we look at very distant galaxies, we are seeing them as they were when the universe was much younger. Light takes time to travel, so distance becomes a kind of time machine. By stitching together galaxies at different distances, astronomers reconstruct a rough timeline. Close by, mature spirals and ellipticals, many already with their star formation slowed or quenched. At intermediate distances, gas-rich disks and merging systems still busy but less frenzied than at the peak. Far away, small, irregular galaxies in the throes of their first major growth, or, earlier still, faint smudges that may host some of the first generations of stars. Across that sequence, you can see entropy's influence. Early on, the universe has plenty of low-entropy fuel, cold gas that can fall into potential wells and ignite. As time passes, more of that fuel is converted into stars, and then into remnants and diffuse hot gas. The process that builds luminous, intricate structures steadily depletes the very gradients that make those structures possible. Cosmic noon, viewed this way, is not just a glorious peak, it is also a turning point. Every star formed in that era is part of both construction and depletion. Each new generation of stars locks away hydrogen, enriches space with heavier elements, and radiates energy into the background, nudging the cosmos a little further down its thermodynamic slope. Where does that leave us? We inhabit a galaxy that likely formed many of its stars during or shortly after that active period. Our Sun is a middle-aged star, born in the quiet tail of that distribution, long after the universe's wildest days of star formation. Our planet assembled from the ashes of earlier stars that lived and died during that busier epoch. The atoms in your body carry, in their composition, a record of that long-ago frenzy. From our vantage point on this one world, the timeline compresses. Human history with writing spans only a few thousand years. The entire existence of our species is measured in a small fraction of a million years. Against the backdrop of cosmic time, those intervals are almost nothing. Yet because we can trace the light from distant galaxies, we are able to infer a story that spans from the first plasma to the crowded peak of star formation and beyond. It is a peculiar privilege. We find ourselves living at a time when the universe is old enough to have written a long history in light, but still young enough that much of that light remains accessible to us. The background glow from recombination is still in a convenient microwave band. The most distant galaxies are still bright enough for our instruments to catch. The signal has not yet been completely stretched and dimmed into undetectability. In the far future, an astronomer in a galaxy like ours might not be able to reconstruct this timeline. As cosmic expansion continues and distant galaxies drift beyond the horizon of detectability, the observable universe of that future observer will shrink. The cosmic microwave background will be redshifted to wavelengths too long and too faint to measure. The evidence for a hot, dense origin will be buried under the weight of absence. From their perspective, the cosmos might look static, eternal, unchanging. The very clues that now tell us about the Big Bang, the Dark Ages, and cosmic noon would be gone. The story of a universe that builds and then undoes its own structure would be much harder to tell. We, for a brief interval, can see both the darkness behind us and the long slope ahead. And if we follow that slope past the peak of star formation and into the declining light, the next question arises almost on its own. In a universe that has already passed its brightest midday, what does it look like when the lamps themselves begin, one by one, to go out? It does not begin with a sudden blackout. It begins with a sky that looks almost the same from one generation to the next, while something slow and irreversible is already shifting behind it. Look at a galaxy in your mind for a moment. A spiral, maybe, like the Milky Way. Bright arms, blue knots of young stars, pinkish regions where gas is lit from within. That is the version we are used to seeing in photographs. But not every galaxy keeps that look. Some of them fade from blue to red, from active to quiet. They still hold stars, but the factory that makes new ones has almost stopped. Astronomers sometimes say that such a galaxy has been quenched. The word sounds violent, like dousing a fire with water, but in many cases, the process is more mundane. Cold gas, the raw material for star birth, becomes harder to come by. Some of it is used up, some of it is heated and stirred by supernovae or by the outflows from a feeding central black hole, so that it no longer settles easily into dense clouds. Some of it is stripped away by interactions with other galaxies or with the thin, hot plasma that fills galaxy clusters. Little by little, the conditions that once made stars in great numbers become rarer. When you compare the universe during its star-forming peak to the universe now, the change is stark. Around the time of cosmic noon, when the cosmos was only a few billion years old, an average galaxy of a given mass was forming new stars between about 10 and about 100 times faster than a comparable galaxy does today. Now, that furious pace has fallen. Many systems, especially the most massive, have joined the red, quenched population. They are not empty, but they are coasting on what they already built. The Milky Way is, for the moment, still in the star-forming camp. It turns some fraction of its remaining gas into new stars each year, but even here, the trend is downward. The reservoir is finite. The laws that govern cooling, collapse, and feedback place limits on how many future generations of stars our galaxy can support. The fireworks cannot go on forever. That general decline is the cosmic backdrop behind a more intimate story, the life of our own star. The Sun was born roughly 4.5 billion years ago from the collapse of a cloud of gas and dust in one of the Milky Way's spiral arms. It settled into the main sequence stage that it still occupies now, quietly fusing hydrogen into helium in its core, releasing energy that holds gravity at bay and lights up the planets circling it. A star like this can remain in that stable hydrogen-burning phase for around 10 billion years in total. That sounds like security, a span so large that it feels almost eternal from our perspective. But the main sequence is not a fixed condition. It is a slow evolution. As hydrogen is converted to helium in the core, the mixture of particles changes. The core contracts slightly, heats up, and the rate of fusion increases. That, in turn, raises the Sun's luminosity. Its brightness today is not quite what it was in its infancy, and it will not remain what it is now. Projections suggest that in roughly 1 to 1.5 billion years, the Sun's gradual brightening will push Earth into a regime that our current biosphere is not built to handle. Increased solar output will intensify weathering and water loss. Greenhouse effects will amplify. Over those long time scales, oceans can begin to evaporate, the climate can be driven into a runaway state, and the surface can become too hot and unstable for complex life as we know it. Long before the Sun dies as a star, the window for creatures like us may already have closed. Further ahead, in about 5 billion years, the core will have converted so much hydrogen to helium that its structure must change. The core will contract, the outer layers will expand and cool, and the Sun will become a red giant. In that swollen phase, its radius will grow to many times its current size. The innermost planets will be scorched, possibly engulfed. Any observer standing where Earth is now would not be standing at all. From the point of view of entropy, each step in the Sun's life is a reshuffling of order into less useful forms. The hydrogen fuel that once could sustain stable fusion for eons is gradually turned into helium and heavier elements, some locked away in the stellar core, some expelled later into space. The light that streams outward each second carries energy away in a form that is easier to disperse than to reconcentrate. The star is not only illuminating its surroundings, it is spending a limited budget of low-entropy fuel. When the red giant phase ends, the Sun will shed its outer layers, leaving behind a white dwarf, a dense, Earth-sized ember made mostly of carbon and oxygen, supported not by fusion, but by quantum pressure. It will be extremely hot at first, then cool and fade over billions of years, radiating away its residual heat into space. The once blazing star will become a slowly dimming cinder. Our star is not an exception. Across the universe, stars follow patterns like this, tuned by their initial mass and composition. Most stars are smaller and cooler than the Sun, red dwarfs that sip their fuel so slowly they can shine for tens or even hundreds of trillions of years. These tiny furnaces are incredibly efficient entropy machines. They take a small, cold gradient and stretch it out over a vast span of time. In the very far future, long after stars like the Sun have passed through their giant phases and settled into white dwarfs or neutron stars, these red dwarfs will still be burning, casting their faint, reddish light into deepening darkness. The night skies of planets orbiting them, if any such worlds remain habitable, would be sparse compared to ours. Fewer bright stars, more small, dull embers. The sky would feel less like a crowded city, more like a quiet village on the edge of a desert. As epochs pass, even those long-lived stars will run down. Hydrogen will become helium. Helium will become heavier nuclei, and in many cases, the remnants will cool into black dwarfs. Theoretical endpoints that are so dim and cold that they are nearly invisible, glowing only in long wavelengths with vanishing intensity. At that stage, the universe will hold many mass points and very little light. Along the way, every category of stellar death leaves its own relics. Massive stars explode as supernovae, forging elements heavier than iron and scattering them into space. Some collapse into neutron stars, matter crushed so densely that atomic nuclei give way to a sea of neutrons. The most massive cores collapse further still, forming black holes from which not even light can escape. Each of these endpoints changes the bookkeeping of usable energy. Gas that is blown out of galaxies by supernova winds and black hole jets is often hot and tenuous. It can take longer than the age of the universe so far for that gas to cool, fall back, and condense into new stars. Matter, locked into white dwarfs, neutron stars, and black holes is, in different ways, harder to tap as a source of low-entropy fuel. The universe still contains mass, but its ability to rearrange that mass into shining, structured objects diminishes. If you zoom out from the fate of individual stars to the gradual transformation of galaxies, the night sky's future becomes clearer. At first, there is plenty of gas to feed star formation. Then the brightest and most massive stars live fast and die young, seeding the medium with heavier elements but also heating and stirring it. Over time, a greater fraction of baryonic matter, the ordinary matter that makes up stars and planets, is tied up in remnants and diffuse, heated gas. Star formation rates decline. Regions of active blue-white light shrink. Redder, older populations dominate. For beings like us, this change is almost invisible. Human lifetimes are too short to notice any dimming of the stars. Even the timescales of recorded history are grains of dust compared to the slow drift of galactic evolution. The same constellations that guided ancient navigators still adorn our skies because the stars that form them have barely moved, barely changed, in the thin sliver of time we have been paying attention. And yet, when you place that thin sliver against the full timeline, you see that we are living after the main chorus of starbirth, in an era where the universe is already spending down its luminous capital. The fact that the sky still looks rich is partly a selection effect. We exist precisely because stars like the Sun formed when they did and have not yet gone out. We are witnesses in the middle of a story, not at the start of a permanent condition. Stories sometimes handle this sense of running out of light by compressing it into a more immediate crisis. In a film like Interstellar, humanity faces failing crops and dust storms on a future Earth. Fields die. Horizons blur under constant haze. The stars become symbols of escape rather than of home. The problem, in that fiction, is not the long-term fate of the cosmos, but an environmental collapse on a timescale close enough to hurt. The emotional resonance is similar, though. There is a shared fear of running out of a future, of living at the end of abundance, with no obvious replacement in sight. In the physical universe, The shortage is not of land or food, but of low-entropy fuel. Star by star, galaxy by galaxy, the stock of easy gradients is being converted into heat and higher entropy forms of matter. There is no malicious intent in this. It is just what the laws permit. Science distinguishes carefully between these levels. The decline in star formation is not a prophecy of imminent planetary failure. It is a description of how the largest structures behave over billions and trillions of years. Our immediate dangers come from choices we make about climate, ecology, and technology, not from the dimming of the Milky Way. But both pictures share the same arrow underneath, gradients being flattened, contrasts being lost. As the night sky slowly loses its brightest lights, what remains is not nothing, but a different kind of universe. One where structure is harder to maintain, where the raw materials for new complexity are scarcer, where more and more of reality settles into forms that change only on absurdly long timescales. A cosmos that, in effect, is starting to forget how busy it once was. And all of this is only one layer of the undoing. The stars can burn out and leave their cold remnants behind. And still, the story is not finished. There is a deeper isolation waiting in the geometry of space itself, a slow stretching that will, given enough time, leave each surviving island of matter increasingly alone. It is one thing for the stars themselves to age and fade. It is something else to realize that, even if they stayed lit, the space between them is quietly learning how to pull them apart. For most of the 20th century, the expectation was almost comforting in its simplicity. The universe is expanding now, yes, but gravity is always there, always pulling. Over very long times, that pull should slow the expansion down. Like throwing a ball upward, it leaves your hand fast, then climbs more slowly, then either pauses and falls back, or drifts on forever at a crawl, depending on how hard you threw it. The details were debated: would the universe eventually recollapse, or coast outward forever? But nearly everyone assumed the expansion was gradually decelerating. Then came a set of exploding stars that quietly contradicted that intuition. In the late 1990s, two groups of astronomers set out to use a particular kind of supernova as a tool. These were Type 1, a supernovae, thermonuclear explosions of white dwarf stars that reach almost the same intrinsic brightness each time. Because they are so luminous and so standard, they can serve as distance markers. Compare how bright they truly are to how bright they appear in the sky, and you can estimate how far away they are. Compare that distance to how much their light has been redshifted by cosmic expansion, and you can trace how fast the universe was stretching when the light began its journey. The plan was straightforward. Measure enough of these distant explosions, plot distance against redshift, and see how strongly gravity had been slowing the expansion over cosmic time. What they found, when the data crystallized, was almost the opposite of what they expected. The distant supernovae were dimmer than they should have been, in a universe whose expansion was gradually breaking. They looked as if they were farther away than such a universe would allow. The simplest reading of that pattern was unnerving. The expansion was not just continuing, it was speeding up. Imagine throwing a ball up from the surface of a world and watching it rise. For a while, it behaves as you expect. It slows as it climbs. Then, midway, it begins to accelerate upward instead, as if some invisible hand had begun to pull it away. That is the kind of reversal the supernova data implied, not for a single object, but for the fabric of space itself. To make room for this behavior, cosmologists revived an old idea with a new name. They called the unknown driving agent dark energy. The word is more a label for ignorance than a description. Whatever dark energy is, it does not clump into galaxies. It does not radiate light. It seems to be a property of space itself, or something that behaves very much like that. In the simplest version, it acts like a cosmological constant, the same energy density in every region of empty space, no matter how much that space expands. The consequences of that simplicity are surprisingly sharp. Ordinary matter, the atoms and dark matter that build stars and galaxies, becomes more dilute as the universe expands. double the size of space, and the same number of particles are now spread through 8 times the volume. Their influence on the expansion weakens. A cosmological constant, by contrast, does not thin out. As space grows, the amount of this dark energy grows with it. The more room there is, the more of it you have. Over cosmic time, that means the balance shifts. In the early universe, matter and radiation dominated the dynamics. Gravity reigned in expansion enough to let structures form. Later, as the universe thinned, dark energy came to the fore. Today, according to our best fits to the data, dark energy accounts for around 70% of the total energy budget of the cosmos. The rest is mostly dark matter, with only a small fraction in the familiar protons, neutrons, and electrons that make up stars and people. From a thermodynamic perspective, dark energy is strange. It acts as if it has negative pressure. In the equations of general relativity, pressure gravitates. It can help pull things together or, in this peculiar case, drive them apart. If you fill a region with a fluid that has negative pressure of the right magnitude, the result is repulsive gravity on large scales. Space does not just drift outward under its own inertia. It accelerates. In 2011, the discovery that cosmic expansion is accelerating was honored with a major physics prize. It was the community's way of saying that this unsettling behavior of the universe is not a curiosity or an error, but a central fact that must be woven into any serious picture of cosmic history. The image that has emerged since is quietly bleak. In a universe where dark energy behaves like a cosmological constant, there are two very different regimes. On small scales inside galaxies, clusters, and other tightly bound systems, gravity still wins. Stars orbit the centers of galaxies. Planets orbit stars. Local structures hold together. On large scales, beyond the reach of binding, dark energy dominates. It pushes galaxy groups apart from one another faster and faster. Right now, we live in a compromise era. The local group, our small community of galaxies, including the Milky Way, Andromeda, and a few dozen dwarf companions, is held together by mutual gravity. Beyond that, there is a broader web of galaxies and clusters linked by thin filaments of dark matter and gas. Light from those structures still reaches us. We can still, with enough patience and collecting area, detect galaxies whose light has traveled for more than 10 billion years to arrive here. Project this forward, with dark energy unchanged, and the view shifts. As expansion accelerates, more and more distant galaxies cross a kind of horizon. It is not a physical wall, but a boundary set by the fact that space between us and them is stretching so quickly that their light will never quite make it here, no matter how long we wait. Photons emitted toward us get carried away by the swelling of space faster than they can reduce the gap. Over vast timescales, the result is isolation. Galaxies outside our gravitationally bound neighborhood recede beyond our ability to see them. Their light is redshifted to wavelengths so long and energies so low that no conceivable detector can pick them up. The cosmic microwave background, already faint and cold, is stretched further. Its temperature falling, its photons diluted. The visible universe for any observer shrinks to the small island of matter that can remain bound against the push of dark energy. From inside such an island, the universe will look deceptively simple. The night sky will contain only the stars of a single galaxy or merged remnant, surrounded by a halo of dark matter and a sparse population of long-dead stellar corpses. Beyond that, apparent emptiness. No external clusters. No cosmic web. No background glow. The evidence that there was ever a Big Bang, an era of radiation, a peak of star formation, will be gone. Not because it never happened, but because the signals have been stretched and swept out of reach. In that sense, dark energy does not just dim the lights, it erases the lines between the chapters. There is something quietly cruel about this, at least from the point of view of curiosity. We find ourselves at a time when the universe is still talkative. It sends us fossil light from its earliest stages. It lets us map the structure of matter over billions of light years. It allows us to infer that its expansion is accelerating. But the same agent that made this discovery necessary is also arranging a future in which no one could ever rediscover it from scratch. The universe is writing its own explanatory notes in disappearing ink. This picture, a cosmological constant in an otherwise standard model, is the simplest fit to current data. But nature does not owe us simplicity. There are hints and tensions that suggest we may not have the full story. Different ways of measuring the current expansion rate of the universe, for instance, give slightly different answers. One set of methods looks at the cosmic microwave background and large-scale structure, effectively reading the story from early times and extrapolating to the present. Another set relies on local measurements: supernovae, variable stars, gravitational lensing, the motions of galaxies nearby. The two families of methods disagree by more than their quoted errors would expect. This discrepancy is often called the Hubble tension. One way to interpret that tension is as a sign that dark energy might not be a simple, unchanging cosmological constant. Perhaps its properties have evolved over time. Perhaps there is some subtle inhomogeneity or anisotropy in the cosmos, a slow rotation, a large-scale gradient, a departure from perfect uniformity that our models have not captured. Maybe our understanding of gravity itself needs refinement on the larger scales. Or maybe the tension will eventually dissolve into better calibrations and more precise data, and the simple picture will survive. From the standpoint of entropy and long-term fate, the details matter less than the trend. As long as there is a component of the universe that acts like dark energy with roughly the observed strength, the broad conclusion holds. Expansion accelerates, distant structures slip away, and the observable universe, for any given island of matter, becomes smaller and more lonely over time. This is another layer of undoing. Gravity once linked galaxies into a vast, connected web. Photons could travel between clusters, carrying information about events across unimaginably large distances. In the accelerated phase, those connections are gradually cut. A cluster here and a cluster there keep their own internal stories, but they cease to be characters in one another's lives. If you think of the cosmos as a kind of social network of matter and light, dark energy is the process that drives it toward fragmentation, not by attacking bonds directly, but by stretching the spaces between nodes until signals can no longer cross. What remains are small, self-contained communities adrift in a darkening, thinning sea. For beings like us, this has two faces. On the one hand, nothing about dark energy threatens our local existence on the timescales that matter for human worries. The acceleration is tiny on the scale of solar systems and galaxies. Our immediate problems, climate, resources, conflict play out over years and centuries, not over the billions of years it will take for the wider universe to recede. On the other hand, the knowledge that this acceleration is real changes the emotional texture of the cosmos. We do not live in a universe that will simply cool and thin while remaining forever interconnected. We live in a universe that, given enough time, will forget its own breadth. A universe where records of the earliest eras are not archived, but gradually redshifted into silence. And this stretching of the gaps is still not the deepest level at which unmaking might operate. Once galaxies are isolated and star formation has dwindled, we are left with remnants. White dwarfs, neutron stars, black holes, cold gas. It is natural, then, to ask a further question. In a universe where expansion never stops and dark energy keeps pushing, are these last pieces of matter safe forever? Or, under the same quiet laws, do even the building blocks themselves begin, one by one, to come apart? If galaxies are destined to drift apart and stars to cool into ash, the next uneasy question is simple enough to phrase: when everything else has faded, do the building blocks themselves still hold? For most of human history, matter looked solid in the most literal sense. Stones, metals, bones. Even when atoms were discovered and the nucleus resolved into protons and neutrons, there was an unspoken assumption that these were the end of the line. You could break things down into smaller pieces, but eventually you would hit something that just is stable, indestructible, except in the most extreme collisions. In the current standard model of particle physics, that stability is almost built in. Protons carry a conserved quantity called baryon number. The equations say that, in ordinary interactions, this number cannot change. If you start with one proton, you must end with one proton's worth of baryon number, rearranged perhaps, but not erased. It is a bookkeeping rule that has survived every accelerator experiment we have managed so far. And yet, many attempts to go beyond that standard model quietly tamper with this rule. Grand unified theories, frameworks that try to merge the strong, weak, and electromagnetic forces into a single, higher symmetry description, often predict that baryon number is not exact. It is approximate. At very high energies, or over very long times, protons may be allowed to transform into lighter particles, positrons, neutrinos, pions. The decay would be fantastically rare, but not forbidden. When theorists work through the details of these models, they arrive at proton lifetimes that make even cosmic timescales look modest. Some early versions suggested half-lives around 10 to the power of 31, or 10 to the power of 32 years. Later, more constrained models tend to predict lifetimes in the realm of 10 to the power of 34 up to 10 to the power of 36 years or more, depending on the decay channel. Those numbers are so large that language struggles with them. The universe itself is only about 1 3/4 times 10 to the power of 10 years old. A proton that survives, on average, for 10 to the power of 34 years is on human scales effectively immortal. But effectively is not the same as absolutely. To test such a faint possibility, you cannot simply watch a single proton and wait. You would never live long enough. And neither would your species or your planet. Instead, you use statistics. If each proton has some tiny probability of decaying in a given year, then a very large collection of protons watched over many years gives you a chance to see at least one of them betray that tendency. This is the logic behind a quiet cathedral of physics buried under a Japanese mountain. Super Kamiokande is a gigantic underground water detector. A cylindrical tank, roughly 40 meters tall and 40 meters across, filled with about 50,000 tons of ultra-pure water and lined with thousands of delicate light sensors. It sits more than a kilometer below the surface, shielded from most of the noise of cosmic rays. Its official purpose is to study neutrinos, the ghost-like particles that stream through everything. But its sheer volume makes it a natural observatory for any process involving the atoms in its water. Every molecule of water contains 2 hydrogen atoms and 1 oxygen atom. Each hydrogen nucleus is a single proton. Each oxygen nucleus is made of protons and neutrons. Count up the total, and you find that the water in Super Kamiokande contains something like 10 to the power of 33 protons. That is a non-intuitive way of saying a lot. Most of the time, nothing remarkable happens. Neutrinos from the sun, from the atmosphere, and from distant supernovae occasionally interact with the water, producing faint cones of blue Cherenkov light that the photomultiplier tubes pick up. Those flashes are rare and beautiful, and they have already rewritten parts of physics by revealing that neutrinos have mass and can oscillate between flavors. But hidden in the same data stream, the experimenters also search for something else: the distinctive signature of a proton falling apart. Each hypothetical decay mode would leave a particular pattern of particles and light in the tank. A proton decaying into a positron and a neutral pion, for example, would produce a short cascade of events with specific energies and directions. Another mode involving a muon and a kaon would trace a different pattern. The analyses are intricate, designed to distinguish such rare events from the far more common background of neutrino interactions and radioactive noise. Decades in, the result is still silence. No clear proton decay signal has been seen. That silence is not empty. It carries information. By failing to see a decay in so many protons over so many years, physicists can set lower bounds on how long protons must live, at least in the simplest decay modes. Current limits for some channels push the proton's lifetime beyond roughly a few times 10 to the power of 34 years at high statistical confidence. In effect, Super Kamiokande and similar experiments have ruled out the more optimistic grand unified models that predicted shorter lifetimes. The theoretical landscape has had to adjust. From an existential point of view, this is a strange way to learn about the future. You sit in the present, watch a vat of water for a few decades, and then extrapolate conclusions about what may or may not happen to matter over spans of time that dwarf the current age of the universe by more than 20 orders of magnitude. It is a kind of statistical time machine made of patience and silence. The uncertainties are still wide. It may be that protons are exactly stable, protected by a deeper symmetry we do not yet understand. It may be that they decay, but only through channels whose probabilities correspond to lifetimes so enormous that no plausible experiment could ever witness one directly. It may be that the relevant physics happens in contexts we cannot reproduce near black holes, in early universe conditions, in regimes where quantum gravity matters. For now, all we can say with confidence is that if protons do decay, they do so exceedingly rarely. Cosmology has to live with that ambiguity. When theorists draw the far future timeline of the universe, they often split it into two branches at this point. In one branch, protons are stable. Neutrons bound in nuclei are effectively stable too. In that case, the baryonic part of the universe, the ordinary matter that makes up stars, planets, dust, and gas, never completely disappears. It changes phase. Stars convert some of it into heavier elements and into radiation. Black holes swallow another fraction. White dwarfs and neutron stars lock their share into degenerate remnants. Over unthinkable spans of time, gravitational interactions can eject some compact objects from galaxies, leaving them to wander intergalactic space. But the protons themselves endure. Even in that scenario, the universe still slides toward a bland end. Stable matter does not mean active matter. White dwarfs cool. Neutron stars lose rotational energy. Black holes, if Hawking's calculations are right, very slowly evaporate by emitting thermal radiation, though that is a story for later. The cosmos becomes a collection of increasingly inert lumps dotted through a thin bath of low-energy photons and neutrinos. Entropy continues to rise. Gradients continue to flatten. But one familiar category, the proton, survives as a kind of fossil. In the other branch, protons are not ultimately safe. Their decay is just too slow for us to see now. Given enough time, a metastable proton will eventually fall apart. In a universe that has already entered its dark, post-stellar era, that decay would be a last, quiet, unmaking. Baryons bound in white dwarfs, neutron stars, rogue planets, and diffuse gas clouds would gradually transmute into lighter particles, electrons or positrons, neutrinos, and gamma rays. Each event would be a tiny release of energy into an already cold environment, a small step toward further uniformity. Over timescales comparable to the proton lifetime, that is, something like 10 to the power of 34 years or more, almost all baryonic matter would be eroded this way. What had once been stars and planets would be reduced to a thin, nearly homogeneous mist of radiation and leptons, diluted further by the ongoing expansion of space. Structures based on nuclei would be erased in favor of more generic debris. This is undoing at a deeper level. It is no longer just the fading of lights or the smoothing out of temperature differences. It is the loss of the very idea of a durable object made of atoms. From our perspective, neither branch makes much difference to daily life. Whether protons last forever or not, our own future is bounded by far nearer constraints. The habitability window of Earth, the lifespan of the Sun, the choices our species makes in the next few centuries. The proton lifetime only asserts itself far beyond any horizon we can personally care about. But at the level of the universe's story, the distinction is real. If protons are stable, some traces of the early universe's specific arrangements can, in principle, persist indefinitely, frozen into relics that never quite dissolve. If they are unstable, then even those traces are eventually washed out. Given enough time, not only will there be no stars or galaxies, there will be no atoms. In laboratories like Super Kamiokande, that question is being asked in the quietest possible way, by listening for a flash of light that has not yet come. The longer the silence lasts, the more extreme the implied patience of matter appears to be. And yet, in either case, the trend remains the same. Whether the undoing stops at the level of structure or continues down to the individual proton, the direction of time still points from more specific arrangements to more generic ones. Beyond that, there is still one more kind of structure that could, for a while, resist the thinning of the universe: the black holes that gather much of the remaining mass into compact, gravitational prisons. If even those begin to leak away, then we reach a point where there is almost nothing left for the cosmos to simplify. Black holes feel like the last place the universe can hide what it has already taken apart. And the unsettling question is whether even those vaults are, in the end, made of time. By the time the cosmos has burned through most of its star-forming fuel, a great deal of ordinary matter has already been sorted. Some of it is locked in white dwarfs and neutron stars. Some drifts as cold gas and dust. But a significant share ends up in black holes, the collapsed cores of massive stars and the supermassive objects that sit in the centers of galaxies. A stellar black hole begins with a star that was too heavy to die gently. When fusion in its core can no longer resist gravity, the outer layers are thrown off in a supernova, and the center falls in on itself. If the mass is high enough, there is no stable state between star and nothing. The collapse continues until space-time around the remnant is so distorted that there is a region from which light cannot escape. That region is bounded by the event horizon. Supermassive black holes grow by a different route, or several routes at once. They may start from heavy seeds in the early universe, swollen by gas falling in and by mergers with other black holes. Over cosmic time, these central giants can accumulate millions to billions of times the mass of the Sunday. When they feed actively, their accretion disks blaze as quasars, outshining their host galaxies. For a long while, black holes were seen as the ultimate sinks. Matter falls in. Information about its detailed arrangement seems to disappear behind the horizon. Nothing, it was thought, can escape. In that picture, these objects are the end of the thermodynamic story. Once energy and matter cross the horizon, they are gone from the observable universe for good. Then, in the mid-1970s, came a calculation that changed the mood. Stephen Hawking, combining ideas from quantum field theory with the curved space-time of general relativity, found that black holes are not completely black. The vacuum near the event horizon is not truly empty. It seethes with quantum fluctuations, pairs of virtual particles appearing and annihilating almost instantly. In the warped geometry around a black hole, there is a small but real chance that one particle in such a pair will fall in, while the other escapes to infinity. To a distant observer, the black hole appears to emit a faint, thermal glow. This is what we now call Hawking radiation. The surprising part is not only that black holes radiate, but that the radiation carries away energy and, by Einstein's relation between mass and energy, reduces the mass of the whole. Small black holes radiate more intensely and lose mass faster. Large ones radiate feebly and change almost not at all on short timescales. But the trend is clear. Left isolated, with nothing to feed on, a black hole will, in principle, very slowly evaporate. The times involved are beyond any intuitive scale. A black hole with roughly the mass of the Sun would take something like 10 to the power of 64 years to evaporate completely. Give it 1,000,000 times the Sun's mass, and the lifetime stretches to around 10 to the power of 76 years. For the monsters in galactic centers, with billions of solar masses, the evaporation time climbs toward around 10 to the power of 90, or even approaching 10 to the power of 100 years. These are rough, order of magnitude estimates, but they are enough to make the point. Black holes are not eternal, only unimaginably patient. In the nearer term, they are anything but quiet. When two black holes orbit each other and spiral inward, they lose energy by emitting gravitational waves, ripples in the fabric of space-time itself. In the middle of the 2010s, an experiment called LIGO recorded such waves directly for the first time, produced by the merger of two stellar mass black holes in a distant galaxy. For a fraction of a second, the power carried away in those waves exceeded the combined light output of all the stars in the observable universe. A collision between two of the universe's darkest objects briefly became its brightest event, in a channel our eyes cannot see. Even that drama, though, is part of the general trend. Two black holes become one heavier black hole plus radiation. More mass is gathered into fewer, larger sinks. More energy is converted into forms that spread and thin as the cosmos expands. If you fast forward through the ages, when stars still shine and galaxies still collide, you eventually arrive at what some physicists call the black hole era. Star formation has dwindled to almost nothing. Most luminous matter has either been used up, locked into remnants, or ejected from galaxies. Over extraordinary timescales, interactions within galaxies and clusters have driven many massive objects toward the centers, where they are swallowed by central black holes or flung outward into intergalactic space by gravitational slingshots. At that stage, the universe's most prominent structures are black holes of various masses, embedded in a very thin soup of radiation and elementary particles. Small black holes may have evaporated already. Intermediate ones are shrinking slowly. The largest behemoths sit nearly unchanged, radiating at temperatures just above absolute zero, leaking energy into a background that is itself cooling. Here, entropy shows one of its strangest faces. Black holes, far from being exceptions to the second law, are, in some sense, its champions. There is a precise formula that assigns an entropy to a black hole proportional to the area of its event horizon. That entropy is enormous. A single supermassive black hole can have more entropy than all the ordinary matter and radiation in its host galaxy combined. When matter falls into a black hole, the horizon area grows, and so does the total entropy. The universe's slide from special to generic continues, just written in horizon area rather than in the mixing of gases or the cooling of coffee. As Hawking radiation carries away energy, the black hole's mass decreases, its radius shrinks, and its temperature rises. This is the opposite of everyday objects, which cool as they lose energy. A black hole, as it evaporates, gets hotter. For most of its lifetime, that temperature is so low that the radiation is insignificant compared to the cosmic background. But as the universe keeps expanding and cooling, there comes a point when the background is colder than the black hole's own temperature. Beyond that, the black hole is no longer in equilibrium with its surroundings. It loses energy faster than it gains it. Evaporation accelerates. In the final stages, for the smaller black holes at least, the process becomes dramatic. As the mass dwindles, the temperature rises sharply, and the power output climbs. The black hole radiates more and more intensely over a shorter and shorter period, ending, in theoretical models, in a kind of high-energy burst. In those last moments, what used to be an object defined by its refusal to let light escape becomes, briefly, a fountain of radiation. For the largest black holes, that finale lies so far in the future that the words before and after feel almost meaningless. To reach timescales of 10 to the power of 90 years, the universe must first pass through epochs in which stars have long since vanished. Protons may or may not have decayed, and dark energy has stretched space to scales that make our current cosmic web look compact. Hawking evaporation is the universe's slowest undoing, working on locks that were designed by gravity to be nearly unbreakable. There is another layer of unease here, centered on information. When something falls into a black hole, what happens to the details of its internal arrangement? Are they lost forever, smeared out over the horizon, or somehow preserved in subtle correlations in the outgoing radiation? This is the so-called information paradox. It has occupied theorists for decades, and while there are promising ideas, holographic principles, quantum error correction metaphors, intricate dualities between gravity and other kinds of field theories, there is still no consensus that everyone would accept as final. From our existential vantage point, the technicalities matter less than the mood they create. Black holes, once thought to be the ultimate guardians of information, may themselves be transitory. Their contents eventually return to the world as featureless heat. If so, then even the most securely buried records in the universe have an expiration date. There is no perfectly safe archive. Combine this with everything that came before, and the long view sharpens. First, the universe expands and cools enough to allow atoms and light to part ways. Then, small fluctuations grow into stars and galaxies. For a few billion years around cosmic noon, star formation surges, building up heavy elements and luminous structures. Gradually, fuel is spent, and the lights dim. Dark energy isolates clusters into lonely islands. Protons may decay, thinning out the remaining matter. Black holes gather much of what is left, sitting as the final, dense punctuation marks at the end of the universe's sentences. And then, given enough time, even those punctuation marks smear out into a uniform line. What remains after the era of black holes is not quite nothing. There is still space-time, still a low-energy bath of photons, neutrinos, and perhaps a sparse population of other light particles. There may still be dark matter particles, if they are stable, drifting through an ever-expanding volume. But the kinds of structures that once punctuated the universe, stars, galaxies, black holes themselves, are gone. The cosmos has very few ways left to change. In that almost featureless future, the arrow of time still exists, but it has very little left to do. Entropy is already close to its maximum, in the sense that most accessible differences have been flattened. There are still more microstates than can be counted, but they all look, from any reasonable distance, the same. Black holes were the last. Deep wells where the universe could hide complexity. If even they evaporate, the notion of undoing reaches its endpoint. There is nothing left to dismantle that has not already been reduced to an almost generic background. And yet, from where we are on a young planet, in a still bright galaxy, in a universe that is noisy with light and structure, this endgame is not a threat. It is a distant boundary condition. What it changes is not our safety, but our sense of what is ultimate. There is no final structure that the universe is tending toward and then keeping. There is only a gradual stripping away of possibilities until all that remains is a kind of cosmic forgetfulness. From that perspective, the question of how the universe ends splits into scenarios that differ in detail but share one theme. Once the locks have evaporated and the archives have faded, is there any sense in which the story can be said to continue at all? Or are we looking at a kind of permanent, quiet dusk, the big freeze, the big rip, or some other variant of a universe that never rewinds, only thins? From here, when we talk about the universe ending, we are really talking about how a story behaves once every character and every lock on their secrets has already been dissolved into background noise. The most conservative picture, the one that falls naturally out of the standard cosmological model, is often called heat death or the big freeze. It does not involve explosions, or a final tearing, or a sudden cut to black. It is a long, slow, almost indifferent fading. In this scenario, dark energy behaves like a true cosmological constant. Expansion keeps accelerating, but never becomes violent enough to rip apart galaxies or atoms that are already bound. Gravity does its local work. Dark energy runs the large-scale show. The two simply occupy different layers of reality. The sequence is, in principle, straightforward. First, star formation dwindles and stops. Over a span of time roughly comparable to 10 raised to the power of 14 years after the Big Bang, the last long-lived red dwarfs exhaust their fuel and go dark. The universe has no new sources of starlight to replace them. Their remnants, white dwarfs, neutron stars, black dwarfs remain, cooling and coasting. On longer timescales, gravitational interactions within galaxies and clusters slowly reshuffle these remnants. Some are kicked out into intergalactic space. Some spiral inward and merge or fall into black holes. over something like 10 raised to the power of 19, or 10 raised to the power of 20 years. Many bound systems are either swallowed or dispersed. After that, if protons are unstable, their eventual decay thins out the remaining baryonic matter over timescales around 10 raised to the power of 34 years and beyond. If protons are stable, they simply sit, locked into compact objects and cold debris, while other processes take over. Then comes the era dominated by black holes. These structures persist for durations that make even the proton lifetime feel modest. A black hole of roughly 1 solar mass would take of order 10, raised to the power of 64 years to evaporate through Hawking radiation. Supermassive black holes in galactic centers, with millions or billions of solar masses, can require up to around 10 raised to something like the power of 90 or even approaching the power of 100 years to disappear completely. During all of this, the universe keeps expanding. Radiation from Hawking, evaporation, and from any remaining particle processes is stretched to longer and longer wavelengths. The average temperature of the cosmos falls asymptotically toward absolute zero. The density of any remaining particles decreases as the volume grows. Collisions become rarer. Events become less common, less dramatic. Further apart in both space and time, once the last black hole has evaporated, what remains is sometimes called the dark era. There are still particles. There are still quantum fluctuations. There is still a geometry of space-time, but from any reasonable distance, it all looks like a cold, nearly empty bath of very low-energy photons, neutrinos, and perhaps other light, stable particles. Entropy is already so close to its maximum that there are very few interesting gradients left to run down. That is the big freeze. No catastrophic final moment, no reset, just a universe that has lost almost all of its ability to produce and maintain structure, coasting in silence. There are, however, stranger endings that begin from the same observation we used earlier. The expansion is not merely coasting, it is accelerating. That acceleration depends on the nature of dark energy, often described by a parameter called its equation of state. A simple cosmological constant corresponds to a particular value, a pressure equal in magnitude and opposite in sign to its energy density. But the universe is under no obligation to pick that exact value. If dark energy has an equation of state slightly more negative than that, something less than -1, cosmologists call it phantom energy. In such models, the energy density of dark energy does not stay constant as space expands. It actually increases. The more space there is, the more repulsive energy fills it. Expansion responds by speeding up faster and faster. Follow that logic far enough, and you arrive at the Big Rip. In a Big Rip scenario, there is a finite time in the future when the scale factor of the universe becomes infinite. Instead of slow, graceful stretching, you get runaway acceleration. Structures that were once safe from cosmic expansion because their own gravity or other binding forces held them together eventually find that the background stretch has grown strong enough on their scale to pull them apart. The timeline is often described in a chilling way. Long before the final singular moment, galaxy clusters lose their cohesion. Their member galaxies are carried away from one another, unable to remain bound. Closer to the end, individual galaxies themselves are torn apart. Stars no longer orbit their centers, but drift away as the fabric of space between them is pulled. Still closer, planetary systems unravel, their orbits no longer stable in the quickly changing expansion. In some versions of the calculation, you can put rough intervals on this cascade. Perhaps a few billion years before the final rip, clusters disintegrate. A few 100 million years before, galaxies are shredded. A few million years out, stellar systems unbind. In the last hours or minutes, planets are torn apart. And in the final fractions of a second, even atoms are pulled apart, electrons ripped from nuclei as the pace of expansion diverges. The exact numbers depend delicately on how far below -1 the equation of state actually lies. Observations so far suggest that dark energy is very close to a true cosmological constant within current uncertainties, so a dramatic big rip is not the favored option. But the possibility reveals something important. The same negative pressure that quietly isolates galaxies in the simple picture can, if tuned just a little more extreme, become strong enough to erase all bound structure outright. If the big freeze is a slow fading of a story into silence, the big rip is more like a page that tears itself apart while you are still reading it. There is also the old opposite of expansion, the big crunch. In a purely matter-dominated universe without dark energy, the fate of everything depends on the average density. If there is enough matter, gravity eventually wins over expansion, slowing it to a halt and then reversing it. The universe contracts, heats, and becomes denser over time, ending in a state that, from one perspective, mirrors the Big Bang. If there is too little matter, expansion never stops, and the universe coasts forever, thinning out. Introduce dark energy, and this neat dichotomy becomes harder to maintain. As far as current observations can tell, the total energy density, including dark energy, is close to the critical value that makes spatial geometry nearly flat. But because dark energy does not dilute like matter, its influence grows as the universe expands. Under these conditions, a genuine recollapse seems unlikely. That has not stopped people from imagining more complex, cyclic possibilities. Some models propose that dark energy might change sign or nature in the far future, turning from repulsive to attractive and triggering a contraction phase. Others suggest that the Big Bang may itself have been a bounce from a prior contracting universe, with entropy somehow reset or diverted along the way. There are scenarios where our apparent beginning is just one turn in an endless series of expansions and crunches. The problem, once again, is entropy. If each cycle simply carries forward the entropy of the last, then subsequent bounces would start from higher and higher disorder. Eventually, there would be no room for an arrow of time that looks like ours. Any viable cyclic model has to find a way to dilute, expel, or otherwise manage entropy, so that the observable patch of the next universe begins in a low entropy state. That is a tall order, and no proposal has yet secured both mathematical elegance and observational support. From a storytelling perspective, these different endgames rhyme more than they differ. Freeze, rip, crunch, or some more exotic variation. None of them naturally produce a clean rewind of the same film. They do not promise a universe that cycles through identical histories, bringing back the same galaxies, the same lives, the same conversations. They are, in different ways, about limits, on structure, on memory, on the ability of the cosmos to keep itself interesting. Fiction often cheats those limits in order to make them emotionally manageable. Asimov's imagined supercomputer, asked how to reverse entropy, eventually finds a loophole that looks like a new creation. A villain like Thanos in a superhero film decides that the solution to finite resources is to erase half of all life with a single act, as if the universe were a ledger and balance could be restored by one brutal subtraction. Both stories use cosmic stakes to dramatize human anxieties about scarcity and loss. Physics is less dramatic and more indifferent. It does not provide a single moment of decision. A lever that, once pulled, decides the fate of all things. It offers trends, constraints, and possibilities. The Big Freeze, based on our current best measurements of dark energy and matter, is the default. The Big Rip lurks as a more violent variant if those measurements shift. The Big Crunch and cyclic alternatives remain mathematically intriguing, but observationally disfavored. None of them, however, carry a built-in mechanism to restore what is undone. What they share is this: once the universe has lost the capacity to form and maintain complex structure, it does not spontaneously regain it. There is no natural reset that brings back a rich, low entropy beginning from a high entropy end. Undoing, in these scenarios, is not a prelude to the same story starting over. It is a gradual loss of the ability to tell stories at all. From where we are, that realization does not need to provoke panic. The timescales on which these endgames unfold are so vast that, compared to them, the entire existence of life on Earth is not even a blink. Whether the universe freezes, rips, or crunches is almost irrelevant to the practical questions that face a species that may or may not survive its next few centuries. What it does change is the background mood of existence. If the universe is not heading toward a stable, meaningful final configuration, if it is instead slowly erasing its own capacity for difference, then the only places where meaning can be held are the temporary patterns that arise along the way. Galaxies, biospheres, minds, cultures, all of them brief arrangements in a medium that, given enough time, tends toward forgetfulness. And on that slope, we are somewhere in the middle. The universe is old enough to have a past worth reconstructing, young enough that the evidence of that past has not redshifted out of reach. The cosmic web still exists. The microwave afterglow is still detectable. The lights in the sky still form familiar patterns. Before we look at how that middle position fits into the full trajectory, there is one more question to sit with. If all of this is the long arc, where exactly are we on it, and what kind of moment have we been born into? If the universe is a long, single exhale, we are living somewhere between the first bright rush of breath and the point where it becomes too thin to feel on the skin. We can start with a simple comparison that does not feel simple at all. The universe has been expanding and changing for something like 14 billion years. The sun has been burning for a little under half of that. Our species, in anything like its current form, has existed for a few 100,000 years. The span of recorded history, the part that fits into books, inscriptions, and digital archives, is measured in only a few thousand. The entire life of the internet is a few decades. The time you have lived so far is some even smaller, fragile slice of that. On the scale of cosmic time, each step down that ladder is a rounding error. From the universe's point of view, the difference between 100 years and 1,000 is almost nothing. And yet, we experience our 100 years, if we are lucky enough to have them, as everything. From this vantage point, it is easy to feel that we are early. The night sky is still crowded. The Milky Way is still familiar. Galaxies still shine at every distance our telescopes can probe. It does not look like a universe that has already done most of its making. But when we place ourselves on the star formation curve, the picture shifts. Cosmic noon, the era when the universe formed new stars at its peak rate, happened when the cosmos was only a few billion years old. Since then, the average pace of star birth has declined by roughly an order of magnitude or more. We are living in a long tail, not the main burst. If you imagine the universe as a day, with dawn at the Big Bang and midnight in the far future, cosmic noon is not a metaphor. There really was a period when the lights were coming on everywhere at once, when gas clouds collapsed into stars more often and with more drama than now. We find ourselves in the late afternoon of that day. There is still light, still warmth, but the most intense building phase has passed. Our own solar system is a product of that declining frenzy. The sun formed from recycled material, gas enriched by earlier generations of stars that had already lived and died. Planets condensed from a disk of dust and rock laced with heavy elements forged in supernovae and stellar winds. In that sense, even our beginning was someone else's debris. The moon taxes our sense of time. To look at it is to see an object that has orbited Earth for over 4 billion years. The continents under your feet have drifted, fused, and broken apart multiple times in that span. Species have appeared, flourished, and vanished. Entire lineages have risen and fallen without ever suspecting that the faint band of the Milky Way above them was a galaxy at all. The night sky we know is a recent understanding, not a recent reality. From the point of view of the larger structure, we live in a modest neighborhood. The Milky Way is not an especially large or small galaxy. It belongs to a small collection called the Local Group, a few major galaxies and many dwarf companions held together by mutual gravity. Beyond that lies a larger arrangement, sometimes called a supercluster, in which our group is just one knot among many in the cosmic web. For a while, it was taken as almost certain that the Milky Way and the Andromeda Galaxy would collide head-on in some billions of years, merging into a larger, elliptical system. Refinements to our measurements have added nuance. The motion is not perfectly aimed. The future encounter may be more of a near miss or a complex dance than a simple crash, and the Sun itself will be changing dramatically by then. In any case, whatever happens between the two galaxies will unfold on timescales long after Earth has likely ceased to be hospitable. This is a useful reminder. Galactic events, even when they sound dramatic, are not aligned with our survival clock. Our more pressing deadlines come from closer and quieter changes. The Sun's very slow brightening is one of those. Left alone, without any interventions by distant descendants, the increasing solar output will probably push Earth past a threshold in roughly 1 billion to 1.5 billion years. Oceans may boil, the carbonate-silicate cycle that regulates carbon dioxide may fail, and the surface may become too hot for complex, surface-dwelling life. This is far beyond human planning horizons, but it is much sooner than the death of the Sun itself as a star. The comfortable window we have inherited is not the permanent baseline, it is the middle of a curve. On even shorter timescales, the things that shape our lives are almost microscopic compared to cosmic events. Climate shifts over centuries, ecological changes across decades, political, economic, and cultural transformations in years or less. Our anxieties inhabit slices of time that the universe barely registers, but those slices are where any meaning we experience actually lives. Against this, our observational position is oddly privileged. Right now, we can still see the cosmic microwave background. Its photons have been traveling since the universe was a few 100,000 years old, redshifted and cooled into microwaves that our instruments can detect. We can still see distant galaxies whose light left them when the universe was young, letting us reconstruct a rough history of star formation and structure growth. We can still measure the expansion of the cosmos using supernovae, galaxy clustering, and subtle distortions in the microwave background itself. In the far future, an observer in a galaxy like ours may not have that luxury. As dark energy continues to accelerate expansion, more and more distant galaxies will cross the cosmic horizon. Their light will never reach that future astronomer. The microwave background will be stretched to wavelengths so long and energies so low that no practical detector could register it above local noise. With only the stars of a single, isolated galaxy to study, they might reasonably conclude that the universe is static and eternal, with no evidence of a hot, dense origin. We, by contrast, live in a narrow window, when the universe is old enough to have produced fossils of its own past, but not yet so old that those fossils have vanished. We can read the afterglow of the Big Bang and the clustering of galaxies as records, like tree rings or ice cores, and infer a story that runs from near featureless plasma to the structured web of matter we see now. At the same time, our own tools are young and incomplete. Telescopes like those orbiting Earth today, and the large mirrors on the ground, have only been operating for a tiny fraction of human history. Instruments that measure gravitational waves or detect high-energy neutrinos are newer still. We are in an early phase of ability, looking out at a universe that is in a middle phase of evolution. There is a tension there. The cosmos has already done most of the work needed to make beings like us possible. It is well past its most active building period. Yet, the particular kind of intelligence that can reconstruct that history and worry about its end has appeared only very recently. If intelligent life arises elsewhere, it will always be in the same situation, emerging late, in planetary pockets, after most of the irreversible thermodynamic moves have been made. One way to describe our position is this: we are not special in size, place, or duration, but we are unusual in information density. In a few centuries, one small species has compressed enormous amounts of cosmic history into theories, datasets, simulations, and art. We have taken starlight and turned it into narratives. We have taken faint microwaves and turned them into maps. We have taken the geometry of space-time and turned it into predictions about a future none of us will see. That concentration is temporary. The servers that store our data, the materials that hold our books and images, the languages in which we frame meaning. All of these are vulnerable on timescales far shorter than those of stellar or galactic evolution. Without constant maintenance and copying, information rots. Formats become unreadable. Media decay. Civilizations forget and restart. Seen from the outside, our moment is a brief spike in the universe's ability to know itself. This does not make us central. It makes us contingent. We live at a time when there is still enough low-entropy fuel left for planets, ecosystems, and minds. And when the sky still contains the clues needed to piece together the larger trajectory. We are late enough that the universe has a story to tell, early enough that it has not yet erased its own opening chapters. On the curve of cosmic undoing, that feels like a saddle point. Behind us lies the climb from a remarkably ordered beginning to a universe buzzing with structure, contrast, and possibility. Ahead lies the descent into thinning light, isolation, and eventual simplicity. We are balanced on that ridge, with a limited view in both directions, trying to decide what it means to live here. From a strictly physical standpoint, nothing in the universe cares how we answer. Entropy will continue to increase. Expansion will continue. Stars will age according to their masses. Black holes will do what black holes do. The curve does not bend for us. But from the standpoint of conscious experience, our position matters. It defines what we can know, what we can influence, and what kinds of questions feel urgent rather than abstract. We cannot choose the shape of the universal trajectory. We can choose how we use the small stretch of it we occupy. That is what leads naturally into the last layer of this story. If we live in a universe that is, on every scale, gradually unmaking its own structures, and if our brief moment happens to be one in which the universe can still be read and still be changed locally, then what follows is not a physics question. It is something more intimate and, in its own way, more difficult. In a cosmos that does not preserve meaning for us, how should a human life be lived? If the universe will not keep anything for us, then the question of how to live stops being a search for the correct ending and becomes something closer to deciding what to do in a room you already know you will have to leave. Long before telescopes and particle accelerators, people were already haunted by the sense that nothing holds. Whole traditions were built around it. In some of the oldest teachings, the idea is almost brutally simple. Everything that arises passes away. Bodies, feelings, relationships, kingdoms, mountains, even heavens and hells, if you believe in them, are said to be temporary stations rather than final addresses. Impermanence is not a bug in the system. It is the system. Cosmology did not set out to confirm that mood. It began with careful measurements of light, with lenses and glass plates and radio antennas, and yet, by following those measurements honestly, it ended up painting a picture that rhymes with those old intuitions. Not only people and cities, but stars and galaxies and black holes are temporary patterns in a universe that slowly loses its ability to make patterns at all. The overlap is almost uncomfortable. On one side, quiet, ancient voices saying, "Do not cling." On the other, satellites and equations saying, "Nothing is clingable anyway." There is a temptation, in the face of that, to reach for a story that restores a sense of destiny. Something like, the universe is unmaking itself so that it can become something better, or return to purity, or ascend to a higher state. That kind of storyline is very human. It bends everything back toward purpose, but nothing in the data insists on it. The curve we see goes from an incredibly tidy beginning to an incredibly bland end, with a burst of complexity in between, and then silence. If there is a hidden intention in that, it does not declare itself through the physics. So we are left with something harder and more honest. Meaning, if it exists, is not guaranteed by the universe. It has to be made in spite of the universe. That may sound bleak, but it also clears away a subtle pressure. If there is no cosmic script you are required to fulfill, then there is no failure in not living up to it. There is only the question of what you choose to pay attention to during the short interval when you are able to pay attention at all. Stories notice this before we do. Think about that film where Earth is failing, dust in every room, crops collapsing, the sky turned into a dull, choking blur. The plot sends a small group of people out through a wormhole to search for another habitable world. On the surface, it is about survival, but underneath, it is about what someone owes to the future and what they owe to the people they love in the present. The main character leaves his family to try to win some tiny sliver of extra time for the species. His child feels abandoned. The film lives in that tension, between duty to a collective future and loyalty to a single life. Cosmic stakes are a way of amplifying an ordinary dilemma. Do we put our energy into repairs we will never see finished, or into the moments right in front of us? Another, more blunt story imagines a villain who looks at finite resources and decides the answer is to erase half of all life with a single gesture. His logic is twisted, but recognizable. If there is not enough to go around, he thinks, then remove mouths rather than questioning the system that produces scarcity. The fear underneath is the same, that there will not be enough future for everyone. Cosmology quietly undermines that kind of panic and that kind of cruelty at the same time. On the one hand, it admits that resources really are finite in the deepest sense. There is a limited amount of low-entropy fuel. There is a limit to how long stars can burn and planets can stay habitable. There is a limit to how long any structure can hold before the universal slope toward disorder has its way. There is no infinite reserve somewhere off stage. On the other hand, the timescales on which those limits become absolute are so huge that they should not distort our ethics. We do not need to erase half of anything to make the universe last. The universe will last far beyond any sane planning horizon, no matter what we do. Our decisions operate on the scales of tens and hundreds of years, maybe thousands if we are unusually farsighted. The cosmic endgame sits out at 10 to the power of 14 years for the last stars, 10 to the power of 34 or more for proton decay if it happens, 10 to the power of 100 for the last black holes. Those spans are not our responsibility. So when someone says, if everything ends, nothing matters, they are skipping over the only region where the word matters has any content. The finite stretch where choices still change experiences. If you watch a film that lasts 2 hours, you do not stand up halfway through and say, the characters will be gone when this ends. So their struggles mean nothing. The ending is precisely what makes the scenes matter. They are not infinite. They are placed. A human life is more like that than like an endless stream. It has a beginning you did not choose, and an end you can only partly influence. Within it, there are scenes you do not control, and scenes you do. Some arcs you can take responsibility for. Others you can only witness. Meaning, in that frame, does not come from extending the film indefinitely. It comes from how the scenes connect, how honestly they are played, how much attention is brought to them. Translating that back up to the cosmic scale. One way to think of a life is as a brief pattern that pushes against entropy locally, leaving traces in its wake. Those traces can be as small as memories in a few other minds, as subtle as a change in how someone treats their child after a conversation, as concrete as a bridge or a piece of music or a new way of understanding a disease. None of them lasts forever. All of them are real while they last. The universe will not archive them for you. But while they exist, they shape the experience of sentient beings inside the universe. That is not nothing. Viewed this way, responsibility does not vanish when you accept cosmic impermanence. It sharpens. You do not have to live for eternity. You have to live for the next minute, the next day, the next decade, knowing that those are the only canvases on which you can actually paint. Heat death is not an excuse to ignore climate change. Proton decay is not an excuse to ignore inequality. The Big Rip, if it ever happened, would not justify turning away from someone in pain beside you now. The scales do not connect that way. Our problems live in the range from the individual heartbeat up to maybe a few generations. That is where decisions bite. If the universe is unmaking itself, The question becomes, how do you want to behave inside something that does not last? One answer is to try to cling harder, to build monuments, empires, legacies that feel less fragile than a single body. Another is to give up, to treat nothing as serious, because nothing is permanent. Both are understandable. Both miss something. Clinging forgets that even the largest structures crumble. Giving up forgets that the depth of an experience is not measured by how long its physical trace persists. There is a quieter path in between, where you accept that every structure is temporary and still care about how it is built and how it feels from the inside.